I'm gonna make a joke for anyone who watches this outside of class. I'll just be like, welcome back to my YouTube channel. Here are my favorite memes of the week, because they're always existing in this class. If 2020 was a math problem, if you're going down a river at 2 miles per hour and your canoe loses a wheel, how much pancake mix would you need to reshingle your roof? Yeah, complex, guys. Dad joke 101. My first ride on an elevator was an uplifting experience. My second ride was a letdown. Ha ha. This is the stupid thing because like usually in a class I can see your guys' reactions, so I'm just imagining good things. Also, I found this really cool video. This 90-year-old woman does a double backflip. It's like ridiculous. What? Sorry, profane, but anyways, I thought it was hilarious. Okay, hopefully you're smiling because I can't see your faces. It's okay, woman, we don't need to see it again. All right, so we're back. Yay, lectures again. Hopefully the last couple weeks were a nice small break from activities and lessened your workload a little bit other than studying. Now we're getting into a little bit more complex stuff for the content of the class. So today is like a nice, easy, not an easy, but it's a nice, gentle introduction into what the rest of the class is going to be, and you'll kind of get a glimpse of different tests we'll be running. But this is if you understand any lecture this semester, this is the one, okay? Because everything in this lecture is based on statistical inference, which is the entire point of statistics in the first place, okay? So with that being said, we're going to start with estimating sampling error. Okay, so questions for the class. What are different things that we want to consider when we collect samples?
One is to make sure the sample represents the population.
Exactly, right? Sample needs to be a subset of whatever the population of interest is, so it needs to be representative of that. How do we collect samples? Or why do we collect samples? That we kind of already answered the why, but what's a big thing that we commented on? I think it was in one of the first lectures.
Is it random sampling?
Bingo. Okay. So samples, two big things. Samples need to be random, right? Meaning there's equal opportunity for anyone in the population of interest to be involved. And then that sample should also be representative of the population that we are studying. All of this plays into statistical inference, right? Or if we want to name this another thing, it's the generalizability of your study. Okay, so the whole purpose that we find a representative sample is because we hardly will ever be able to measure an entire population, right? So if we're confident that our sample is representative of our population, we can draw off of the sample characteristics and say a population would be very similar to this, okay? With a sample, though, there comes some degree of sampling error. And we call this the amount of error in the estimate of a population parameter based on a sample statistic. So again, because we can never have an entire population, we're always going to be estimating what the population mean would be based off of our sample mean. Or we could also measure other things of the population, but we're primarily looking at how closely does the sample relate to a population, or how closely can we estimate a population or population information based off of a given sample. There always is some inherent amount of error, right? Just because our sample is always going to be smaller than our population size. But this is kind of like the key of today's lecture. And then obviously there's going to be more stuff. But sampling error generally is referred to as standard error. Okay. So in this case, we're going to be looking, in at least today's lecture, we're going to be looking at the standard error of the mean. But if you guys kind of reflect back to when we talked about shapes of distributions and we calculated the z-score of skewness and kurtosis, there was a standard error portion in our calculation, right? That square root of 6 or 24 divided by n. So that was the way that we standardized our sample statistic to our population. It'll be the same case in today's lecture where we're using standard error of the mean. So largely what we're going to be looking at is how do we estimate a population mean or a true population mean from a given sample mean that we get from whatever procedures we're using. So this is a formula you will want to know, and I'll put it on, I think it's actually already on your activity for this week. But standard deviation is represented by SD. N represents the sample size. Okay, so in order to kind of draw some relationships about how this is going to, or how these values are going to interact with the population, or estimation of the population, I think a big hitting point for a lot of people is like you need a very large sample size when you collect data. And this is one of the reasons, right? Because you can see N is inversely related to the standard error. So the larger the N you have, the less standard error you're kind of bound to get. So we can reduce standard error, which is kind of the goal. The less standard error we have, the better of an indication that our sample information is closer to what actually exists in the population. So increasing sample size will decrease standard error. And then also decreasing our variability in our sample can decrease standard error. And this primarily is going to come with a larger sample size, right? The more people we have, the more representative our sample is of our population. Therefore, there should be inherently lower deviations within that sample. Okay, so you can think of standard error as a standard deviation for a population, if that makes more sense, right? Standard deviation is like itself for a sample, okay? But if we took, and maybe this might make more sense in the next slide, but if we took a bunch of random samples, right, each of these little plus signs is going to represent some sample mean out of a population. Okay, so this is kind of how statistics works. Remember, we always assume a population has a normal distribution, but that normal distribution comes about by taking a bunch of sample means and placing them right within a given distribution based on the population of interest. So again, this graph is representing the frequency distribution of sample means. Okay. And then basically what we do with all these sample means is we estimate a population mean off of them, right? So again, standard error, right? If you think like 1 standard deviation, 2 standard deviations, or 3 standard deviations, right? Standard error is just how many standard deviations from the population mean a particular value is. So with this, in statistics, you probably have seen something called the level of confidence and alpha. These two things go together, okay? So assuming our population is normally distributed, we also assume that or we have to meet the assumption that our sample is normally distributed, so we can infer, right? We saw with one of the examples before exam 1 that when the shape is different, where we had like a negatively skewed example one of the times, right? If our shape of our sample is too far off of normal, it's really hard to draw conclusions about the population, or there's different elements that can get skewed with those outliers present. But let's say that we have a normal sample, a normal population, okay? We call a certain area a level of confidence, okay? And this basically means like this is the area we think the mean will fall into, okay? The area outside of that, right? So where results are going to be assumed to be different, right, or considered different from the mean are going to be our alpha regions. Okay, we also call this the region of rejection. And I think I touch on this a little bit later. Yes, I do. So I'll wait until we get there. But this level of confidence and the alpha are basically equal to 100. When we look at, remember, percentile view is 0 is over here, 100 is over here. So adding whatever this area is plus this area plus this area is going to give us 100. So that's kind of a big part in understanding how these equations work. So again, level of confidence is going to be as a percentage, okay? And it's basically just establishing the area under the curve at which we would say the null hypothesis is correct, okay? So remember that when we test hypotheses, it's always innocent until proven guilty, or there is no relationship or no effect until we can prove there is one, right? So usually this level of confidence is going to be fairly large because we need a fair amount of certainty, right, that something is actually different between two means or different between two groups, etc. Okay, so the way that we calculate our level of confidence is 1 minus alpha, because alpha is going to be represented as a value between 0 and 1. Okay, so if we do 1 minus that times 100, we end up getting a percentage of our level of confidence. We can reverse this equation and do 1 minus the level of confidence, or 100 minus the level of confidence. Either way, alpha is and level of confidence are going to be directly equal to each other, direct differences from 100%. Okay. Just another clarification. Level of confidence is always a percentage. Alpha is always going to be a decimal number between 0 and 1. Okay. And so, again, remember we said the alpha region is our rejection, or area of rejection, or region of rejection, right? So this is where we're considering there's some probability of error. So a lot of times you'll see like P is less than 0.05, right? Or we've kind of touched on P before. P just represents a probability, and it's usually the same as alpha. Its comparative number is alpha. So this is going to represent the chance, right, that the null hypothesis is incorrect, in which you would reject the null and accept your research hypothesis. Okay, so it's probability of being wrong due to chance occurrences that aren't controlled. So this could be an instigative of a cause and effect relationship. It could be instigative of a certain type of correlation between different factors, right? So usually when we have P less than alpha, we would say we have a significant difference. And I'll go into that once we get our figures up. But examples of this would be, usually you'll see a 90% level of confidence associated with alpha of 0.1, which if we turn this into a percentage, it's 10%, right? So 90 plus 10% is 100%. The most common level of confidence you'll see is 95%, right, associated with an alpha of 0.05. And then lastly, a more liberal level of confidence is going to be 99%, right? So really wide interval with a very small degree of error, okay, which would be 0.01. So this kind of is a good segue into hypothesis testing. We're going to be jumping around a little bit, but I promise it'll all come back together. Anthony, I saw your question. We are getting there. That's why I segued into the hypothesis testing. So hold your question for a second. I'll see if I can answer it. So with hypothesis testing, remember we always have a research hypothesis, which is what we're predicting the outcome to be. And we always have a null hypothesis, which is mutually exclusive to the research hypothesis, right? And it's stating there's no effect or no relationship, kind of depending on the statistical test we're running, okay? Hypotheses can be split into two options. There's non-directional hypotheses. So we've seen examples of this before where we're either saying, like our null hypothesis would say there's no difference, right, between means. Mean 1 is equal to mean 2. No effect of an intervention, no relationship, etc., right? Then the research hypothesis is going to say there is some difference. Doesn't matter if mean 1 is greater than mean 2 or less than mean 2, we just know there's a difference, okay? If we want to specify a direction, we call it a directional hypothesis, and that would be where we say greater than, less than, right? And the research hypothesis, so if we think one training method is going to be more effective in improving strength than a control group, I don't know, right? You're specifying a direction though, okay? So these come into play for what we call tailed tests, okay? So when you have a non-directional hypothesis where we said, I can jump back to this, non-directional, we're saying means are equal, right? And if you're trying to prove the null or the research hypothesis, you're basically just trying to say there is a difference. Could be mean 1 is greater than mean 2, mean 1 is less than mean 2, but that's where we get the two alphas, okay? So there's regions of error on the upside and the downside of whatever your level of confidence is, okay? So when we do this, right, because let's say we have a 95% level of confidence in the center, what would alpha be equal to? (95%) means alpha is
5%.
5%, right? But because we have a region of rejection below the mean as well as a region of rejection above the mean, that means we have to have alpha divided by 2, okay? Because if we did 95% in here and then went and said 5% and 5%, that's not equal to 100, okay? So what we have to do when we have a two-tailed test, which is basically going to be the most common test that we run in this class. Actually, it's the only type of test we'll run in this class. You're going to have to do alpha divided by 2. So if this is a 95% confidence interval in the center, or level of confidence in the center, we would say this is 0.025, and this is 0.025, representing 2.5%, 2.5%, add them together, you get 5%, okay? We have a different case when we look at a one-tailed test, okay? So because we're specifying a certain direction, our level of confidence is going to include, let's say in this case, we chose a 90% level of confidence. That would include everything in this region, okay? And then if we have a 90% level of confidence, what would alpha be?
%5.
90% level of confidence?
10%, 0.1.
10%, there we go. right? So we would say all of our allowable error is going to be on one side. So this whole thing would be 10%. And the same would go if our alpha was on the other side. Okay. So with this, it's important to understand how to, well, I guess, yeah, it's important to understand it kind of primarily on this two-tailed test that you're looking at alpha divided by 2, because this will help us when we look at z-scores. Yes, they're coming back. Okay. So based on whatever your alpha level is, right, you can imagine when we look at these pictures, alpha is, I like to go off the negative side because it's directly related to a z-score, right? So we have the area to the left is representative of alpha. So in, let's say this is a 95% level of confidence, right? This entire alpha would be equal to 5%. So z-scores are going to come into play because we have to know how far away from the mean are we saying alpha is located, right? So if I stop sharing really quick and we look at our z-table, which I just assumed you guys could see, and I didn't share my screen, that's dumb. All right, so if we look at our z-table, right, on the negative end, because we're saying over here, right, one tail, 95%, alpha is going to be equal to 5%. So if we look at this, you know the probabilities down here represent the area under the curve. So we're going to be looking for a value in here that is as close to 0.05 as possible, right, but not surpassing it. So in this case, that would be, oh no, that's all of the values. In this case, we would choose this one here. So that's negative 1.65. Okay. The reason we don't go above 0.05 is because if we're saying I'm accepting a 5% amount of error, right? If you overestimate, that means you could possibly be including erroneous data, basically. Okay. If we underestimate slightly on where this alpha would be located, then we're technically just making it a little bit harder to prove ourselves wrong, or to prove the null hypothesis wrong, right? But that's a good thing because the less error that we allow, the more accurate our results are kind of going to indicate, okay? When we're doing a two-tailed test though, right, so if I pop back to this example, we have, again, alpha divided by 2. So this is where it becomes important you understand how to read the z-table in relation to a two-tailed test, right? Because if this is a 95% level of confidence, alpha is going to be 5%, and we divide it by 2 regions of rejection, so that'll be 2.5%. Or if we're looking in our z-table, it would be 0.025, right? We're looking for the closest value to 0.025. And in this case, we get it nice and easy. It's exactly equal to 0.025 at a z-score of negative 1.96. Okay, so these z-scores are going to be important in some different equations that we're going to be looking at. And remember, z-scores just indicate how far away a given score is from the mean, right? Because it's equivalent to a standard deviation. So this brings us into our question of p-values, right? Do we accept or reject? Okay, because p-value, remember, is the probability that the null hypothesis is incorrect, right? Or it's going to be associated with our alpha. So usually that's when we say if p is greater than alpha, there's a high probability, right, that a type 1 error has set in. And type 1 error is just another fancy word for alpha. Okay. So it basically means if P is representing an erroneous region, right? If we have a high p-value, right, or alpha is alpha is set, right? This isn't changing. So let's say we have 0.05 as our alpha. If the p-value is greater than that, that means we have a high probability of error. And if that's the case, we want to accept the null hypothesis because we don't have a small enough error or a small enough confidence that we have actually achieved significant results. Okay. When the p-value is less than alpha, that means we have a low probability of error. So this is when we reject the null and we declare statistical significance. Okay. So just to put this into perspective, because I like drawing, if you have, I'll just do a building of this, right? If this is a mean, we say some level of confidence, let's choose 95, right? We're going to say that we expect 95% of our sample to be in this area, okay? So this is representative of, I'll say 95%, so this is our level of confidence, right? And this is going to be the region where we would accept a null hypothesis, right? So we'll get into this a little bit more when we look at t-tests or ANOVAs, but let's say we're trying to estimate a population mean and we actually know the population mean, right? So we take a sample, we get a sample mean, and then we try to relay it back onto the population, okay? We're basically saying there's a 95% chance that based on the sample we've collected, it's going to land in here. Or here, sorry, reaching bad aim, okay? If we have, maybe we're doing an intervention and we're trying to prove that this intervention is sufficient enough to change particular results with regards to the sample, right? That's where our research hypothesis region comes in. So this is this area right where alpha is located. Let's say we have a two-tailed test, so alpha is going to be these regions here, okay? If we're doing an intervention and we're trying to prove a sample is different from a population or that the intervention is effective, right? If our sample mean happens to land in this area or this area, right, that indicates we need to reject the null hypothesis because the degree or probability of error is really low, okay? So I think this figure usually starts making sense by about the 5th time I show it to you. So if it doesn't make sense, yep, it's okay, but hopefully it will make sense soon. Okay. Are there any questions so far? I probably have just like shot all of you and you're like, ah! Okay, so this pulls us back into our confidence interval. Okay, that was a quick detour, but organization of this lecture always gets me. I've probably changed it every single semester. So confidence intervals are directly related to our level of confidence, right? So I'm gonna stop sharing for a second. When we calculate a confidence interval based off of a sample, right, the confidence interval is going to be indicated here. Okay, so this area from the boundaries of our level of confidence, however that translates to our sample data, is going to represent our confidence interval. So this is confidence interval. Okay. You guys can see that okay, right? Okay, cool. Okay, let's share. So you will also need to know this formula. And like I said, for this week, we're going to be calculating a confidence interval for a true population mean given sample data. Okay, so you can see the sample mean indicated by X bar, and then Z-score comes in, right? And this Z is going to be relative to the level of confidence that you choose. All right, so I have an example here. If we have a level of confidence of 95%, this means our alpha is 5%. Assuming that we're in a two-tailed test, alpha on both tails would be 2.5%, right? Which we actually just looked up, gives us a z-score of plus or minus 1.96. Okay, plus or minus because we have one alpha tail on each side. Okay, when we note our confidence interval, it's going to be the lower bound listed first, followed by the upper bound. We put it in brackets to indicate that we're including the values in this coordinate, basically. Okay. So what we're doing is we say the population of interest, right? Let's say we're looking at the ages of individuals that live in mobile home parks, right? And maybe we go to different mobile home parks and we end up sampling 50 people. Okay, we end up getting a sample mean of 60 with a standard deviation of 5 years. Okay, we're assuming we have normally distributed data because that's the only way that we can infer this on our population. And usually in situations where you're collecting numerical data, you'd have to run your z-score of skewness and kurtosis to figure out that you're actually normally distributed. And then to find the lower bound of the interval, you would use the lower end, right, of your z-score, so the minus side, and then for the upper bound, you use the positive z-score, okay, which should make sense because of the distribution, right? Negatives on the lower side of the mean, positives are on the upper side of the mean. So in this case, if we calculated it out, we would have the sample mean, which is 60, right? Our z-score we determined is 1.96, right? Plus or minus, based on the level of confidence that we've chosen. And then the standard error of the mean, remember, is the standard deviation divided by the square root of the sample. So this would be 60 divided by the square root of 5. Okay, so we're going to practice this on the next slide. That way you guys aren't looking at me like I'm totally nuts. Okay, so on the bottom you should have a link. This should take you to Beachboard if you click on your PowerPoint. I'm going to stop sharing for a second. Change the sharing settings is what I want to do. So we're going to do this in Excel. I think that's the simplest place to try it out. Let me find mine. Okay, so you should have something that looks like this. I'm going to check the participant list. Does everybody have this? Can answer yes or no. If you need more time, that's mainly what I want to know if you don't have it downloaded yet.
Yeah, I downloaded it, but somehow it's not opening up in my computer.
Okay, so if you can't get it or pull it up, just follow along on the screen and then try doing it later if you can figure out why it's not pulling up. Okay, so our first example we're going to say is pertaining to VO2 max. That's a really common measurement we'll use in this class all the time. But let's say our sample mean is 60, and we're calculating confidence intervals with the following conditions. Okay, so this exercise is primarily to help you calculate standard error of the mean and confidence intervals, but also to demonstrate how these change, or how the confidence intervals will change based on different elements. So in this case, all you're going to do is type 40, 20, 60, and 100 in the sample size box. So 40, 20, 60, and 100. Standard deviation is 4, 3, 5, and 5. Okay, and then our standard error we have to calculate, which I'm gonna move this over, right, is standard deviation divided by the square root of the sample size. So we just do equals standard deviation divided by the square root of the sample size. Okay, I'll take a pause just so you guys can get your stuff typed in. Okay, and then this should be a copyable equation. So you can just copy it down and you have your standard error calculated for each of these different sample sizes. Next thing we have to figure out is our z-score. Okay, so in our first sample, we're using a 90% level of confidence, right? And then I've inserted this table to kind of help you guys out so you know what the z-score is that's associated with a level of confidence and a given probability of error, or p-value. Okay. So generally we could say this is also alpha. So if you guys want to make a note on that. But if we're using a 90% level of confidence, that means we have an alpha of 10% or 0.10. Okay. If we're using a two-tailed test, alpha would be what probability in the tails? Assuming we have a two-tailed test.
5% for each side.
5% for each side. So if we look up 0.05 in the z table, right, particularly on the negative z table, we should get 1.65 as our z-score. Okay, so in this first box, you're going to put 1.65. The plus or minus is going to come in when you do your actual calculations, so just put a positive value. Okay. If we have a 95% level of confidence, that means we have an alpha of 0.05. Divided by 2 would be 0.025. And if we look 0.025 up in the z table, we get 1.96. So that's what's going to go in these two. And then lastly, we have our fourth sample, which was a 99% level of confidence. That's going to be associated with a p-value or alpha of 0.01. Divided by 2 is 0.005, which is associated with 2.58 z-scores. Okay. So now we have all of the elements that we need to calculate our confidence interval. So this will be the lower end, or if I pop back, right, lower bound, upper bound, or lower CI, upper CI. Okay. So in this case, our lower confidence interval can be found by doing the sample mean minus the z-score at a given alpha times the standard error. So we just plug this in through here. Our mean was indicated as 60. That's not going to change, so we can just keep that as a constant. we do minus, and then order of operations should take care of this. So if you put z times se, that's totally fine. I like to put mine in parentheses because it organizes it. But you'll have z times the standard error. Okay, and that should give you the lower end. The upper end, if you want to just copy in the formula box and do it this way, because if you don't, it'll try to carry your cell references over, right? And instead of minus, we're just going to do plus. And that gives us our upper end of our confidence interval. Okay. So in order to calculate the interval size, does anyone have any ideas on how we might do this? Kind of similar to grouped frequency distributions.
Maybe take the bound difference.
Take the bound difference, right? Because this is going to be different from grouped frequencies because one of our values is not included in a group frequency. Because we've got confidence intervals have those brackets, we're including both values in the interval. So we can just take the difference, right, between the upper and the lower bound of the interval to get the interval size. Okay, so fancy schmancy, all of these, bing, calculated. Okay. So this is a good start. The only thing we're going to do different is you're going to copy all of this data, paste it down below, because this is when a sample mean is 60. Now we're going to do an example of when the sample mean is 50. So the only thing that should change is the confidence interval calculation. Remember, standard error is just standard deviation in the sample mean. Okay, so all that's going to change in here is 50 and 50. And then you should be able to copy that function to give you new intervals. Okay. And like I said, you guys will get practice with this in the activity. So if you haven't caught up, don't worry about it. Just look at the screen for now. Okay, and we'll see what happens. So I'm kind of gonna toggle between screens. Okay, when we do a mean increase or decrease, okay, so when we change the mean from 60 to 50, okay, you're looking at what happens to the confidence interval. In this case, the actual values, right, if you take the difference between 58.96 and 48.96, it was a shift to the right. Okay. So if we change the mean, let's say if we increase the mean, we're going to have a shift to the left. If we decrease the mean, we have a shift to the right. The reason this happens is because standard deviation is not changing, right? A standard error is not changing, so the variability around the mean is still the same in these two situations. But what's happening is the center of the interval, which is the mean, right, is changing. So that's what causes the shift to right or left. If we change the sample size, okay, remember we said sample size is directly going to affect the standard error. So let's say if we increase the sample size, that should decrease the standard error, which goes into this formula. If we decrease the standard error, that means the magnitude of this portion of the equation is going to get tighter. Okay, so you can see as we increase in any of these examples, right, as we increase our sample size, you can see that our values here are going to tighten. Okay, so increasing sample size should narrow the confidence interval. Okay, where you can really see this difference is in 3 and 4 because the deviation is the same for each of these. Okay, so 2.53 to 2.58. Wait, what? That's dumb. That should narrow. It should get smaller. I don't think I have a wrong reference. Odd. Basically, why it's supposed to narrow, I'm gonna look into this and I'll get back to you guys. But the confidence interval should narrow because we're going to be increasing the density of values in the center of the distribution, basically. Okay, so the more people we have from our population, the more confident or the tighter our interval should be centered around the mean, if that makes sense. So if we decrease n, that would cause a spread of our interval. So I'll look into that, but I feel like we did the math right, but that doesn't make sense on why that didn't shift properly. And then the last relationship I wanted for you guys to look at was the level of confidence. Okay. So when the level of confidence increases, in this case, we had a 90% level of confidence, 95 was in the middle, 99 was at the end. Okay. When we increase the level of confidence, that widens. Oh, and that would explain why this is different. Okay, never mind. I got it. We're good. So I will explain. I'm sorry. When the level of confidence increases, you can think about it as our, right, we set like, we're 95% sure our mean is going to land between point A and point B, right? If we increase that distance, and this, you can see this directly with the z-scores, right? If you increase from 90% to 95%, you've added another, 0.3-ish people that are deviated from the mean, right? So that would indicate you're including more variability within your sample data. And then the same thing goes if we extend out to 99%, right? We're going to be including more and more people. So that's why that relationship didn't work out the way that I wanted it to, as far as population increasing. What really would have been the good example was looking at this one, because sample size, even though the standard deviations are different, right, they were based on the same level of confidence of 95%. So you can see as we increase sample size, not changing the confidence or level of confidence is going to result in a narrower interval size. That's what I was trying to say. All right. So many rules, you guys. But I would really kind of like look into this a little bit more. If you want to make up different scenarios, that's totally fine. The activity you have this week would be a good way to, test these things out. But these are level of confidence, the sample size, and the mean are going to be the main factors that are going to affect the interval. Okay. Standard deviation is going to also have an effect in some degree, but it's not going to be as much as, say, like sample size or the mean. Okay. So then we come into this idea of how are these values determined? Okay, and it's the researcher who decides. So it's it's a it depends type of answer, um, which isn't always acceptable to students, but it's just based on how much error you're willing to accept. So usually, and we'll go into a little bit more on error, but usually people would say, like, you want to choose a 99% level of confidence, right? Because the probability of making an error needs to be really, really small in order for you to reject the null. So in that case, you would be very, very certain if you had a p-value less than 0.01, right? You have a very high degree of certainty that you have disproven the null hypothesis, or that you're accepting your research hypothesis, right? But you also have to remember what happens to the confidence interval when the level of confidence increases, and that's that the interval size is going to widen, right? Because you're going to be including 99% of the distribution. Okay, so usually there's this trade-off relationship between our level of confidence and our alpha, right? If we increase the level of confidence, p or alpha is going to decrease, right? Which means our interval is going to broaden. So that's the idea that we're widening, right? And that generally is going to mean we're going to be less precise in a way that we may be including people who are actually significantly different from our population, okay? If we do the other direction, right, it's a complete inverse of what we just said. So if level of confidence decreases, or say we are going from 95 to 90, right, P is going to increase because our rejection is on the outside, right? So as we close our interval down, we're including less of the population in our null hypothesis area and more people in the region of rejection area, okay? In which case P is increasing, right? The confidence interval narrows. And in that case, the interval is going to be more precise because it's smaller, right? Versus a large window or a large interval, which is less precise because there's more variability that's being included. Okay. Have I lost anybody? I should clear responses before I ask that question. Okay. I swear to God, this will make sense in time. Usually hits home by the time we get to ANOVAs, but I'm always very determined to make it work. Okay, so those are important relationships, again, that you should be aware of, at least on that that slide before this one. Okay, so I'm gonna shift gears for a second. I know we're over time that we're allotted for the class, so if you have to take off, totally fine. We pretty much just have to talk about error. Okay, so we end up with this thing called the Orwellian sounding truth table. Someone named Orwellian came up with it. But basically, it's a variation of different combinations, right? Or a table of different combinations. Think about like biology and phenotypes or whatever, right? So we have different situations where we accept the null hypothesis and different situations when we reject the null. Namely, when P is less, or P is greater than alpha and P is less than alpha, right? But we also have situations where we would say the null is true and the null is false, okay? The problem is that this is an indication of research results, and we never actually know what is going on in this area of the table. Okay, that's the whole point of research. So in the case that we accept the null and the null is true, that would be a very good choice, right? Because those statements agree with each other. Okay, if a research results say accept the null hypothesis, there's too much error to reject the null, right? We would say, okay, then the null is true, right? These two agree with each other. In the case where we reject the null hypothesis, meaning we think the probability of error or the probability that the null is wrong, right? We have a small degree of error, basically, is how that translates, but the null is actually true. This is where we get our type 1 error, otherwise known as alpha, right? So that region of rejection is why we refer to it as an erroneous area, right? Because it's representing the chance or the probability that we guessed wrong, okay? So this would be representative of a false positive, right? Saying that, yes, we rejected the null, but we're actually wrong, okay? So this would be when we say there's a relationship or effect between the independent variable and dependent variable, and there actually is no relationship or no effect, okay? If we come back to the table and we say we get a p-value greater than our alpha that we set, right? In that case, we would accept the null hypothesis. But in whatever case we're working with, the null is actually false, okay? This is also an erroneous pairing, okay? If we accept the null hypothesis when we should actually reject it, we call it a type 2 error, also noted by the Greek letter beta. Okay, so this would be a false negative. Okay. So this would be saying we accept the null hypothesis, saying there's no relationship or no effect, right, between independent variables or dependent variables. Could also be between different independent variables if we have a control group versus an intervention group, right? But we're accepting the null, saying there's no effect, when in actuality there is one, okay? This type of error can be controlled by using statistical power, okay? And this can be controlled in a pilot testing type of situation where you figure out the sample size that you need to boost your power high enough that you decrease beta. So power is going to be associated with the last box in this truth table, where we have a good decision of rejecting the null and the null is false, right? So reject the null or say there is an effect when in reality there actually is an effect, right? So these two are going to be direct opposites of each other, which is why we can say 1 minus beta gives us our power, right? And we'll mess with some calculations that look at power a little bit later when it means more to us, okay? But just to give you a pictorial type of idea here, right? Again, power is going to be when we reject the null when the null is false, okay? Best way to increase power is to increase sample size, okay? If we increase our sample size, remember we input degrees of freedom, okay? So that's going to increase our degrees of freedom. This means that the more people we have, the taller, right, this peak is going to be, because we're going to be adding more people to the center of the distribution if our sample is representative of our population. That also means that our confidence interval narrows, right? Because remember we said we increase sample size, it narrows the interval, so we're more precise, right, in the sense that our mean is going to be very close to either lower or upper bounds of our interval, okay? But that also means it's going to be easier to reject the null when the null is false, because if this interval here is narrowing, that means that this is getting bigger, okay? So that's one thing to remember when we look at types of error, right, is you can only commit one type of error at a time per statistical decision, okay? So when you look at the table, you're either choosing correctly by accepting the null, or you're choosing correctly by rejecting the null, okay? If the null is true and the null is false, respectively. But if we have alpha versus beta, right, they're complete opposite decisions. So you can only make one type of error at a time. The sucky thing about this is that you never know what type of error you've committed, okay? So this is where repetition of different experiments is going to be super, super important, okay? The other thing to remember is if you don't prove significance, right, where you're not going to reject the null because you have a high degree or a high probability of error, it's not necessarily a bad thing, right? Because non-significant findings can be significant in a way that you prove there was no relationship or no effect between two different variables, okay? So I think that's one thing researchers sometimes get stuck in is they're like, I wanted to prove it wrong, you know? And it's not always gonna be the case, okay? So then there's the concept of how we control error, and this is gonna be our tail end of our discussion today. I have a hair hanging off of me and it's really bugging me. But basically, because you can only make one type of error at a time, you decide which one is most important to you, and then you protect that. So for type 1 error, right, which is our alpha down here, if you want to protect the chance of incorrectly rejecting the null, then you want to use a more conservative alpha, right? Meaning you make the alpha smaller so that it's harder to reject the null hypothesis, right? And this would be in the case of if we have a corrective surgery, right? Obviously, before we make that a common practice, we need to be absolutely certain that it's going to work or produce the results that we want to, okay? So obviously we wouldn't want to say this surgery is effective when it actually is not effective, okay? On the flip side, if we're looking at type 2 error, okay, this is when we say I'm accepting the null, but the null is false. Okay, if you want to protect against those chances or those odds, you would want to use a more liberal alpha. Okay, because this is going to come in with your interval, right? If alpha's on one side, beta's going to be on the other side. They're completely opposite decisions. Okay, so if we're looking at the effectiveness of drug on treating a cancer, right, that would require we want to be more precise with our interval in the sense that it's narrower, right, around the mean. So if we're narrowing our interval, that means we increase our alpha, right, or increase the chance of error. So again, there's this like give or take. Is it like, do we want to be precise or is it okay to be less precise? Because it's going to be advantageous in both scenarios, which is why most people usually say just use 95% because it's in the middle, okay? But ultimately, again, it's up to the researcher what you do. And the way that we figure this out is study replication. Okay, so again, finding out if you actually made an error is by redoing the experiment over and over and over and over and over again. Okay, so wrapping it up, right? How do you know what test to use? And this is all going to come in once you figure out what your research question is, what variables you're using, who you're sampling, right? This is all going to give us information, right, at how we're going to run statistics, okay? So the first thing I'm always going to ask you guys when I give you a research scenario is figure out what types of variables are being dealt with, okay? And these are our typical categories. So you're either going to have nominal data or ratio data in this class. So you can kind of cancel out the concept of ordinal and interval data. They don't mean anything to us anymore, okay? Within our decision trees that we're using, we're always going to refer to nominal data as non-parametric. So because non-parametric also includes ordinal, that's why we refer to it as more of a general term. But from here on out, nominal and non-parametric are synonymous with each other, okay? Whenever we're using quantitative data, right, we're always going to use ratio in this class, no interval. So again, put it out of your head. okay? Remember, we called ratio and interval data parametric. So now parametric and ratio are going to be synonymous with each other, okay? So first you figure out what types of variables are being dealt with. So this is identifying independent, dependent variables, how many levels, etc. Then you want to figure out, kind of just said that, then you're going to figure out who you're measuring. So when you have a within subjects design or a paired samples design, every subject is going to be used, okay? Or they're all going to be measured. So if we're looking at the effects of study time on exam performance, okay? Maybe in this case, we have people study for exam 1 for 3 hours, and then they take the test. And then for exam 2, we say study for 6 hours, and then they take the test, right? And then exam 3, they study for 9 hours, and then they take the test. And then we would be comparing exams 1, 2, and 3 to each other. But we use the same subjects for each measurement. So we call that within subject study design. When we use different subjects, so same example, right? We're looking at 3, 6, and 9 hours. Let's say I had 3 different sections of Kin 483, right? And each class I would control, like section 1, you only study for 3 hours. Section 2, you guys only study for 6 hours. And section 3, you only study for 9 hours. And then we'll compare everyone's test scores together, right? And see if there are any significant differences between how long you study and what score you get on the exam. Okay, so if you're using different subjects within the groups that you're measuring, we call that a between subject design. Okay, the last thing you have to make sure is that you meet test assumptions, right? So meeting normality, meaning there's no outliers. Also making sure you have random sampling. And another common thing that we're going to be talking about is that you have equal variance, right? So if I have one sample as a standard deviation of 4, arbitrary number, and I have another sample that has a standard deviation of 40, one of those samples is not representative of the population, right? Because there's way too much of a spread between our values. So making sure you have relatively equal spreads of your data is really important. And usually that'll be covered with the normality part, but because we allow a little bit of flexibility between like -2 and +2 on our z-scores of skewness and kurtosis, there's going to be some error in this equal variance. And we have corrections that will take care of those in our statistical tests. But basically, these are all the things you have to figure out before you decide what test to run. This is a flow chart of what tests we'll be doing, okay? So again, you're looking at type of data for your dependent variable, type of data for your independent variable, how many independent variables, how many levels of that independent variable, and that'll end up telling you, right, if you're using between or within subjects, right, all of these factors tell you what test you're going to run. Okay, so next week we get to mess with regressions and correlations. And then within this next exam, we'll talk about t-tests as well as ANOVAs. These two are going to be in the 3rd exam. Okay, I used to go over clinical measures in chi-square, but they're a lot less applicable to this field. At least I didn't think they were as important of an emphasis. Kind of took us off track, and I think there's a little bit more commonality between this whole bottom row. Okay, so these are all the tests you guys are going to learn. In addition, there's 3 different types of factorial ANOVAs, and we don't even have on here that you have multiple dependent variables. Those are MANOVAs, M meaning multiple. So now we're into the grit of the class. Okay. Do you guys have any questions before we depart for the week? Good. Thanks for hanging in there. Activities posted. I'll hopefully get this up later this evening so you can do a rewatch if you want to rewatch. And then, yeah, you guys are free to go.
Thank you.
You're welcome.